Which of the following functions have a fixed doubling time, a fixed half-life? In A, we're given the function y is equal to 6 times 2 to the x. Let's use a graphing calculator to explore this function. Go to y equals to enter the function 6 times 2 to the x. Go to table set to set up a table, second window. I'm going to suggest that we use a table start of 0 to determine the initial quantity and then increment by 1 to get an idea of how the function behaves. Leave the independent and dependent variable on auto so that the table is automatically filled in for you. Then go to table, which is second graph. In this case, we can see that the initial quantity is 6 and the y values are increasing. How long does it take for 6 to double to 12? Well, we see that it just takes 1 unit of x. As x increases from 0 to 1, the y value doubles from 6 to 12. How long does it take for 12 to double to 24? Well, we see that it takes just 1 more unit of x. As x increases from 1 to 2, the y value doubles from 12 to 24. In fact, every time that x goes up by 1, the y value doubles. So this function has a fixed doubling time, and that fixed doubling time is 1 unit of x. For part B, we're given the function y is equal to 5 plus 2x. So let's go to y equals, clear out our old function, and enter the new function 5 plus 2x. Go back to our table, and this time we see that the initial quantity is 5. The y values are increasing. How long does it take for 5 to double to 10? Well, 10 is halfway between 9 and 11, and so it will take between 2 and 3 units of x for the quantity to double. Since this is a linear function, it'll take 2.5 units of x for the function to double. So let's go back to table set and see if there is a fixed doubling time. We'll let table start remain at 0, but we'll increment by 2.5 since it took 2.5 units of x for the quantity to double from 5 to 10. Go back to our table, and what we want to do is to check and see if for every increase of 2.5 units in x, the y value doubles. Well, we see that initially it doubles from 5 to 10, but it doesn't then double from 10 to 20. It increases by 5 from 10 to 15. Instead of taking 2.5 units to double, it takes an additional 5 units to double. So this function does not have a fixed doubling time, because as x goes up by 2.5, y doubles initially, but then it doesn't double from then on. For part C, we're given the function q is equal to 300 times 1/2 raised to the t. So go to y equals, clear out the old function, enter the new function using x as the independent variable rather than t. So enter 300 times 1/2 raised to the x. Set up a table using a table start of 0 and an increment of 1. View the table. Notice now that the initial quantity is 300, and instead of the y values increasing, the y values are decreasing. So this time we'll be looking to see if this function has a fixed half-life. How long does it take for 300 to be cut in half to 150? Well, it takes just 1 unit of x. How long does it take for 150 to be cut in half to 75? Well, it takes just 1 more unit of x. Every time that x goes up by 1 unit, the y value is cut in half. Therefore, this function has a fixed half-life.